All right, let's get started. Let's do the bi-weekly contest 128. Today's contest. Hey, first, Smarter, how's it going? So, score of a string. You're given a string S. The score of a string is defined as the sum of the absolute difference between the ASCII values of adjacent characters. Return the score of S. Okay, so not much to say here. We can do a one-liner in Python. We go over the element starting from the second one, index 1, and we want the absolute difference of the ord, so the ASCII value of s of I minus s, the ord of s of I minus 1, and we want to add this. We want to sum so there's not much to say about this one, I guess. Yeah, let's move on to Q2. Minimum rectangles to cover points. So we're given points in the plane and an integer w, and we have to cover all the points with rectangles. As the title says, and each rectangle has to have its lower end at, so notice that y must be 0 and some x 1, and its upper end at some point. So but we have the restriction that, yes, we have the condition that the distance between x1 and x2 must be less than or equal to w. Okay, a point is considered covered by a rectangle if it lies within or on the boundary of the rectangle. The minimum number of rectangles needed so that each point is covered by at least one rectangle. Okay, so yes, you can cover by more than one rectangle. So here we get an example. So yeah, the first observation here, notice that these rectangles are pretty tall, but notice that we don't have, the only restriction that we have is on the width in the x-axis, but we don't have any restriction on the y-axis, so we can make it as tall, as high as we want, right? So that means that we can ignore the y coordinates of the points. We only care about, so if a point is has an x coordinate that is within the x coordinates of the rectangle, then it will be covered regardless of the y coordinates. So we can ignore the y coordinates. So then the question is, how do we place the rectangle so that we can minimize? So okay, so notice Hey, Strike on Bro. Welcome. So notice that if we consider, so let's consider this as let's say that the points are in order. Remember that we forget about the y coordinates. It is only a line. The smooch guy. Okay, so notice that maybe we have a point here, and so on. We have them order. So notice that we want to place the leftmost rectangle should be, it's pretty easy to realize that it should be here. That the left side should be at the leftmost point that it hasn't been covered yet. Okay? Because obviously, since there are no points to its left that are uncovered, if we put it somewhere to the left, then we could move it back to this position, and we wouldn't the solution would still be optimal, right? And if we put the leftmost rectangle to the right of this point, then x1 won't be covered. So that proves that you can, if we place it at x1, the leftmost, that would give us an optimal solution, right? So then we know that the width is w. So we can then go over all the points, and if they are covered by this rectangle, we skip them, and then we're at the same situation, right? We now have we can ignore all the points that we covered already, and then we have another point here. And so again, we place the rectangle here, and we go over the points that are already covered, and so on. So it's pretty straightforward. So let's sort the points by the x coordinates. So we're gonna have an index. So we're at point I. So we're gonna put the rectangle at x of I, and so how many ways is every way to do Q4? Well, yeah, I could have. So I'm planning to only do my solution, which I think it's simple, but yeah, I could have thought about other ways of doing it, I guess. Anyway, so okay, so now we want to skip all the points that have so if the points of J, the x coordinate is less than or equal to points in I plus W, then we skip it. And so, and every iteration here, we're putting a rectangle. We're placing a rectangle, so we count 1 for each, and then I becomes J because J is the first one that is not covered. And I think this should be it. Let's see. All right. Yep. Pretty straightforward. I think. Any questions about this one? I think I explained it here. I gave the proof of why it's always it's optimal to place the rectangle at the leftmost point that hasn't been covered yet. So the proof is what I said, that if you think about moving it, if it's not there, it's to the left, then you can move it without making the solution worse. All right, so let's move on to Q3. Minimum time to visit disappearing nodes. So you have an undirected graph with weights. So this is pretty standard. And the nodes disappear. You get an array that indicates the time when node I disappears, and you can't visit it after it disappears. And we have to return the answer, an answer array denoting the minimum units of time required to reach node I from node 0. If node is unreachable. Okay, so it's pretty. So you're asked to find the shortest paths from a single source on a weighted graph. So this immediately should you should think about Dijkstra's algorithm. But there is a catch here, the disappearing nodes. But notice that you still want to get to each node on the shortest path. And if the node, when you get to the node and it disappears, then you skip it. You cannot keep going on from that node, of course. So I think it's just a Dijkstra. So let's create our adjacency list. Adjacency list. And we get the distances. Let's set them to infinity first. And then we want what we want the distance to 0 to be 0, and we want a queue, a priority queue, where we have the distance 0 to node 0. And so we have the distance to u and u at the top of the priority queue. And here, if the distance, if the distance is different than the minimum distance that we found, we need to continue. This is standard Dijkstra. But also, let's add here if the node disappeared, so then we also continue. We don't move. We don't continue with that node. And so here, this is just standard Dijkstra. If the new distance, the distance to be is this, so we update it, and now we have all our distances, and we go over all the nodes, and if the distance to u is less than the disappearing time, well, the distance or the time, it doesn't matter. Then we have to return that distance, otherwise we return -1. And this is it. Pretty straightforward Dijkstra algorithm problem. So yes, you gotta keep your you gotta know your Dijkstra. And yeah, I've seen that many people had TLE. I'm not sure why. I've seen cases where they forgot to do this, for example, to check. So notice that in the simple implementation of Dijkstra, when you find a shorter way to get to a node, since you cannot update the value of the key of the B, you just add another value to the heap, right? So you add node B now with a shorter distance. So that means that you have duplicated keys in the heap, and so you don't want to process them more than once. So if once you process the first one, which should be the shortest one, then all the other occurrences should be ignored. I mean, they won't change the answer because the distances won't be better. The distances from a node, if you arrive later than you did before, then those distances won't matter, but it will become slower, and that could make you TLE. So yeah, just Dijkstra. And for this one, Q4, find the number of subarrays. I like problems that have short descriptions. Find the number of subarrays where boundary elements are maximum. And even the title is pretty descriptive. So where the first and the last elements of the subarray are equal to the largest element in the subarray. All right. There is a single subarray. All right, so let's go to the drawing board a little bit. So let's say that we have an array. Let's say we had 5, 3, 4, 5, and then 1, 5, and 6, and so on. Well, now let's do it concrete. Okay, so one way. So you need to count, again, let me remind you, you need to count subarrays. So subarrays are contiguous portions, segments of the array. You should always know the words. These are keywords that are used in LeetCode. Subarray versus, or substring versus subsequence. These are important, and they have specific definitions. In any case, here we care about subarrays, and the first and the last elements are equal to the largest element in the subarray. Stream upgraded to full HD. Anyway, so one strategy, one idea would be to start counting. So let's try to count all the subarrays that start with some number, right? So let's say that we want to count all the subarrays that start at 5, at this position, right? Position 1. So notice that, well, the subarray must end with 5, right? Well, let's say that we want, since it's the beginning element, then the maximum must be 5, and it must end in 5, right? So that means that we could have the subarray that only contains 5, or we could have this subarray that contains this 5 and ends at this 5, or we could have this other subarray, right? And why we extended this? Well, let's say to make it more interesting, that here there is another 5. But notice that we cannot get here, because here we have a 6, and that would we have to extend while 5 is the maximum element of the subarray. So we can use this 5, or this 5 as endpoints, right? So that means that we have 3. We have 3 subarrays that start at this 5. How do we do this systematically? Well, first of all, notice that it's important to find this value, right? The value of the 6, of the first one that is greater. The first one to the right that is greater. And this is called the next greater element. Next greater element. And it's a known problem that can be solved quickly. You can calculate the next greater element for each position in linear time with a stack, with a monotonic stack. So let's say that we already have that. So now once we have this, we only need to count how many 5s there are in this region, right? Those are the ends. So we need to find out how many 5s. Those are the possible ends for this position. So what I did here, so then notice that it doesn't matter here. I don't care when I'm processing this 5 here. This doesn't matter. All I care about are the positions of the 5s and the NGE of position 1. And so maybe we can create a list for each value. So for example, for 5, we can create a list that has the positions. So the first one is at position 1. The second, so this is 2, 3, and 4, then 6, and then 8. And we have this. Once we have this list, then we can process it like a 2-pointer or a sliding window. So for example, when we process, we want to make the starting point of the subarray this element, the one at 1. Then we want to expand the right side until we get to the NGE, which is going to be here the position is 7. So with the right pointer to this position, which is the first one that is greater than or equal to the NGE. And so we just count the difference. So this is at position 0. This is 1, 2, and 3. This is at position 1. So that means that there are 3 minus 1 endpoints for the starting point of 1. Well, 3 minus 0, 0. So it's 3, which is what we counted here. Did you find that position using binary search? Which position? So I create this data structure just by going over and appending using a dictionary. And when I find a 5, I append it to the list of 5. When I find a 3, I append it to the list of 3, and so on. So I'm not using binary search at all. So I'm just gonna be using 2 pointers, and I'm gonna compute the NGE at the beginning. So let's see it in the code. But does that answer your question? So this is pretty standard. So while this is less than or equal to nums of I pop from the stack. And if there is something, it means that I found the NGE of I, of position I. So now I have the next greater element of every position. Now let's make our groups. Let's group. So we group by value and we append the index, right? So now we have the we're gonna process each group or each value, but we don't care about the value anymore. We only care about the index. So we're gonna have a sliding window of R, so R and the left side, and these are going to be indices on the index array, right? So bear with me, it might be a little indirect. So what I was saying is that while there are still elements to the right, and the index of this element is less than the NGE of the index of L, then that means that we have to grow our window to the right, and then we add the difference, and this should be it. The stream is super crisp. That's great. So it passes. Yeah, that's what I didn't worry about thinking about other solutions, because I think this one, I mean, yeah, I should think about them anyways. But yes, no big deal. So yeah, I guess it requires some observations when you realize that you want. Once you realize that you can extend up to the NGE, the next greater element. So if you approach the problem in this way, so you set the starting point of the subarray, then you realize that that value has to be the maximum. So you're limited by the next greater element, in this case 6, and then you realize that you just have to count. So the ending, you just have to count the number of times that value occurs in this range. I guess you could have done it maybe in a different way. I mean, to count this, yeah, I guess you can do binary search, of course, but I was thinking about something such as prefix sums, but yeah, I think it could be a little too memory intensive. Well, I think this makes sense. You have to deal with the indirection that you are dealing with indices of indices, right? Because L and R are indices inside this array, which contains the indices where the value occurred. So that could be using. Yep. Yeah. Once you do this reduction, you realize that you only care about the positions of the 5. I think it's pretty natural to do this representation. With the list of indices. So that's usually a good thing in problem solving. So when you realize that there's information that is irrelevant and that you're capturing, you're capturing all the information that you need to solve the problem in a more compressed form. You're not losing any information, then it usually it might be a good idea to even do it explicitly in the code. Or at least when you're thinking about it. So yes, I share the submission, and yeah, we've done 36 minutes. So last contest, I think, were pretty straightforward. So that's why I've been doing shorter streams, I think. Well, yeah, my bad is that I didn't think about other ways of solving this. That would have been interesting for content. But yeah, this way of thinking about it is so natural to me that I feel it's hard to do something else, because I heard that you can use union find. Well, we'll see. Maybe tomorrow I'll do a longer stream. I'll be more prepared. If there are alternative solutions, I'll think about them before the stream. But yeah, that's all I have for now. No, maybe I can do another stream later or tomorrow if I find them interesting. But the idea of this streams is to explain the solutions that I thought about, so that I can give a good perspective. So yeah, that's all I have. So see you in the next one. Bye bye.